Hello, everybody. This is the video for section 6.4, Green's theorem. Green's theorem can be called the fundamental theorem of calculus in two-dimensional space, otherwise known as the plane. So it is an extension of the other two fundamental theorems we have learned so far, the fundamental theorem of calculus and the fundamental theorem of line integrals, except we have one extra dimension. So with that, without further ado, let's get going. Green's theorem. Okay, so section 6.4 is the first of the three named theorems in section or chapter 6. I should say 4 because we already had the fundamental theorem of line integrals. And the other three are Green's theorem, which we will be discussing today, and then followed by the Stokes theorem, which is one dimension even higher than Green's. And then we will end this chapter with the divergence theorem. All right, so these are some of the main results of calculus 3 vector analysis. And so remember that these are pretty important, results in the area of calculus, especially in vector calculus. All right, so I would as always, I would like to review a concept in calculus 1 first, right? So the fundamental theorem of calculus, remember what this is. And I know there are two parts to this, fundamental theorem, I guess I should say, of calculus. And I am focusing on the second part, which I recently reviewed as well, right? So we have an interval AB, right? And you have this function. And of course, the area of this region is the definite integral from a to b, fx dx. And we write this as f of b minus f of a, right? And where f prime is the lowercase f. So the capital F is called the antiderivative. So let's go ahead and write this. This is antiderivative. And I want you to also remember that A and B are the 2 points that are called the boundary points, okay? In fact, every interval has only two every closed interval has a closed and bounded interval has only two boundary points, right? And so they are called A and B here, okay? And then last time we had the fundamental theorem of line integrals. So basically, that is the version of the fundamental theorem of calculus. We still have a one-dimensional domain, like the closed interval AB, except this time F is of a higher dimension. So what we have is a plane like this, and you have it could be in 3 dimensions as well, but we have a curve C that goes from point A to B, remember? And then the fundamental theorem of line integrals says that f dot t ds, which by the way, this is the work integral, which can be written as, p dx plus q dy, right? Which we can also write as f dr. This is the most common way of writing this. It turns out to be f of b minus f of a, where c is a curve going from a to b. And of course, if the gradient of f is capital F, right? Just like over here, the derivative of capital F was a lowercase f. This time, the gradient, which is sort of like the derivative of the lowercase f, is the given vector field f, okay? You may notice, by the way, the cases have switched here. Here, capital F was the antiderivative. Here, the lowercase f is the sort of an antiderivative, whose derivative or the gradient is the given vector field f. So somebody messed up in here. They should be consistent. They should have been consistent with the cases, but they weren't. Okay, but that's besides the point, right? But the thing I want you to remember is that f is like, here, the capital F is something you have to come up with. You have to find the antiderivative. Over here, you have to find the potential function. This is like, still, I mean, I wouldn't call this exactly the antiderivative, but it's like the antiderivative because the derivative or the gradient of lowercase f is the capital F. All right, and A and B are boundary points. In fact, there are only two boundary points for curve C because curve, by definition, is a one-dimensional object. All right, so now what we do is we upgrade this to a version, the R2 version, okay? So now let's add the dimension to both of these in a sense, okay? And so this is what we know as Green's theorem. And now I will have another version of this because the second version is sort of a tweaking of the first version. But this is what you need to know. If F is a two-dimensional vector field, PQ, and if R is a region with C as its boundary. Now, here's a main difference between the first two I mentioned, the fundamental theorem of calculus and the fundamental theorem of line integrals, and Green's theorem. In Green's theorem, we have the plane, and then now we're going to be talking about a region, R, okay? Because a region is a two-dimensional subset of the plane, you know, the XY plane, the region is two-dimensional, and therefore the boundary is not just 2 points, like in the first two cases. The boundary is actually this entire curve, or a loop, a closed curve. Let me make it even more precise. It's a simple closed curve, right? If region R is closed and bounded and simply connected. Okay, so if R is a region with C as its boundary, which let's just emphasize that it's a loop, it's closed, then okay, we can calculate the work integral, which is, now I write this, let's see, let me just go ahead and write this in the fundamental way, ft ds. This is the work integral, right? In this case, we can call this a circulation integral. I will just mention this, right? And then this can be written as pdx plus qdy. Now, this turns out to be important because this is the version that I'm going to later tweak to get to the second part of Green's theorem, right? But it's right now it's in the parentheses. It's not all that important. It could be written as FDR, right? I know this has a lots of different ways of writing, but the whole point is that this circulation or the work integral is equal to, are you ready for this? The double integral over the region of qx minus py. Yes, these are partial derivatives, and then dA. Now, this is something brand new. You have never seen qx minus py, and so this needs some explanations. So let me add a few comments before we go any further. First of all, okay, this and everything else, of course, you know, this and this, these are all called work integrals, okay? In this case, because the C is a loop, we can call this a circulation integral or flow integral. They all mean the same thing, okay? Basically, it's the FDR integral. And what this is saying is, now, remember, this is a line integral, right? This is a line integral. The second part, the right-hand part is not actually the line integral. This is dx dy or dy dx, or if you use the polar coordinates, it's r dr d theta. This is actually a double integral. So this is kind of weird, right? I'm saying that line integral, a single line integral, is equal to a double integral of something. Okay, now what's qx minus py? All right, so this part later we will learn that this is called the curl of f, but that's not going to come until the next section. So I am not going to talk too much about the curl of f, except in explaining Green's theorem in just a second. But this is the statement of the theorem, which you will need to learn, right? So F is a vector field, two-dimensional vector field. And what this is saying is that the work integral around the boundary, the circulation, the work produced by F around the boundary curve C is equal to the double integral of the curl of F, or Qx minus Py, Okay, and then of course you do dx dy or dy dx or r dr d theta. All right, one more thing I should mention here is this curl. The if you want to just sort of memorize this qx minus py, that's fine. Some people memorize this as quicks minus pay. I don't know what that means, okay? But qx minus py can be memorized by just reciting quicks minus pay, and then you will get this right every single time. All right, so, oh, and by the way, one more thing here. I should mention here that C is counterclockwise oriented, not clockwise, but counterclockwise. Now, the thing is, they had to decide counterclockwise. They had to decide which is the standard notation, right? The orientation, counterclockwise or clockwise. And it was basically a random choice. But because we calculate, we measure angles in trigonometry where we go counterclockwise, it's sort of a standard in mathematics to orient closed circles counterclockwise this way, right? And there, the idea is that the left-hand side, looking from the top, the left-hand side is the inside, okay? Later on, we'll be talking about the flux across C, okay? And when we talk about the flux across C, we always go from the left to the right-hand side of the orientation. So the flux will go from here to here, which is what we would like to have, right? The flux should be going from in to the outside of the region. So anyway, C is, make sure C is oriented counterclockwise. If C were oriented clockwise the other way, then of course it'll be just a negative of what you get over here. Okay, so the in short, the short version of this Green's theorem can be written as this: FDR, the work integral is equal to the double integral of quicks minus pay. Okay, so this is the main part of this. Okay, and and all the other things are just additional details that I must add. All right, let me give you an example. And by the way, you notice here, if this is just a line integral, if it's only a line integral of this curve C or something, which is not a closed loop, then you cannot apply Green's theorem. The Green's theorem assumes that you have a circle, right? So it is very important for you to, I'm not a circle, but a closed loop. So it's very important that every time you are up to apply Green's theorem, you must have a closed region R whose boundary is that curve C. Okay, otherwise you cannot apply Green's theorem. All right, I'll tell you what, the theorem is sort of proved in the book. The rigorous proof is actually beyond the level of calculus 3. The book does have some explanations, which I will sort of add after this example. Okay, let me just give you an example to see how nice this theorem is. Let f be y cubed x cubed plus 3xy square on C, which is C1 union C2, okay? And I will draw a picture of this and then explain what that means. So here's the first example. Let's say C1 is this curve, part of the parabola y is equal to, x squared, okay, just like there, from 0, 0 to 1, 1, followed by the straight line segment coming back from 1, 1 back to 0, 0. So that would be along y is equal to x, going from 1, 1 back to 0, 0. Now notice here C is a C1 followed by C2. And so that is it is a closed circle like this, right? And the region inside is, of course, R. And so the curve C1 union C2, or C1 followed by C2, is actually the boundary. And it is oriented in the correct direction, the positive direction, which is the counterclockwise direction. All right. So now let's find the work integral. So this will be the work. Let me just go ahead and interpret this. This is work done by F on the curve C. So C1 and then C2, right? And so what is the total amount of work done by F as an object moves along C1 and then back to the origin on C2? And let me just give you the old and the new ways. So here's an old way of doing this. Okay, so you have two curves. So we have to parameterize C1 and C2. So let's parameterize C1 first. C1 goes along the parabola. So the most natural way to parameterize C1 is this t comma t square as t goes from 0 to 1, right? Okay, and on there, of course, our f of xy, this is the vector field, and I have this as y cubed comma x cubed plus 3xy square. Let's go ahead and rewrite this. Remember, x is t, y is t squared, right? So this will be t cubed squared, and yeah, okay, comma, and then t cubed plus 3t times t squared squared. Okay, simplifying this, you get t to the 6th power and then t cubed plus, and what do you have here? 3 times t to the 5th, that's t to the 6th again, right? Oh, that would be, no, it's t to the 4th times t, so it's t to the 5th. So that would be the way to write that. And then, f in terms of t. We have to find the derivative because that's how you find FDR. And so this will be 1 to t. Okay, so that would be the derivative here. And then you do f dot r prime because that's what you'll end up integrating. And that's t to the 6th plus 2t to the 4th plus 6t to the 6th. Now, notice here, all I'm doing is taking the dot product of this and this, right? And so this will be 7t to the 6th plus 2t to the 4th. And we get to integrate this. So the integral on C1 of f dr is equal to the integral from 0 to 1 of 7t to the 6th plus 2t to the 4th dt. You should have parentheses here because that's the appropriate way to denote this. And so this is t to the 7th plus 2/5 t to the 5th from 0 to 1. And you can readily see that this is 1 plus 2/5, and that is 7/5. Okay, so that's the first part. Remember, I'm still doing this in the old-fashioned way. Now, C2 is a little tricky because it's kind of going backwards, right? So I don't want actually to do C2 this direction because things get a little messy when you go from 1, 1 to 0, 0. And so, and you do want to go, and there is a way to do this, but it's much easier if you consider a negative C2. That would be going from, this is C2, but the negative C2 goes from 0, 0 to 1, 1. And that's much easier to parameterize, okay, because that's just tt, as t goes from 0 to 1. Make sure you don't go backwards. You don't want let t go from 1 back to 0, okay, because that's going to actually mess up your orientation. All right, so if you are thinking of negative C2, eventually I'm going to just put the negative sign in the end, to find the integral over C2. But this is your R for on the way back, which is your C2, but except you're going the opposite direction, right? Now on this line, fxy, remember fxy is still this thing here, right? So this is y cubed. In this case, it's y and x are both t, so x cubed, and then t cubed, and then the next one is x cubed, which is t cubed, plus 3x y square, where x and y are both t. So you can write f on this line segment as t cubed, comma, and then how many cubes do I have? T cubes do I have? I have t cubed plus 3t squared. That's 4t cubed. All right. R prime is of course 1, 1. So f dot dr turns out to be t cubed plus 4t cubed, otherwise known as 5t cubed. So the integral over the negative of c2 of f dr, remember I'm going backwards, is the integral from 0 to 1 of 5t cubed dt, which is 5 fourth, t to the fourth, going from 0 to 1, and that, of course, is 5 fourth. Okay, and so finally, and so by the way, this means that the integral from in the opposite direction, c2, will be negative 5 fourth, right? I'm just changing the sign because now I'm considering C2 in the correct direction. All right, so the total work done on C is the sum of this number and this number. It's 7/5 minus 5/4. Maybe this is the hardest part for us, you know. Do you remember how to subtract fractions? Okay, well, let's see. I know I can do this. All right, just make sure I just tell myself, hey, I can do this. I can do this. That's 2. Okay, so this is 28 over 20 minus 25 over 20, and the answer is 320, 20th. Okay, so that is the total work done by F along C1 joined by C2. The old way. Okay, you see, it took me like more than half a page to do this, right? So here is the new way to do this, all right? And so this is the one that uses, of course, by Green's theorem. Green is a mathematician, a British mathematician that is credited with this method and the proof of this theorem. It has nothing to do with the color of vector field or anything like that. But according to Green's theorem, right, this integral, f dr, the circulation integral or the work integral, is the same as the double integral. And by the way, this is why we have chapter 6 after chapter 5, because you have to know how to take double integrals before you before we go into a chapter on Green's theorem. This is what we are looking for, all right? And so now we have to figure out what that is. All right, so we have this region R, right? And I know how to define this region R, or you know how to do that because you studied chapter 5 very, very hard, okay? It's a region sandwiched between x squared and y is equal to x squared and y is equal to x, right? And so we need to know what qx and py are. All right, so let's try to figure this out. Remember, f was y cubed, x cubed plus 3xy squared. Now, when we write it this way, you know this is p and this is q. No problem here. So qx is 3x squared plus 3y squared, right? All you're doing is taking the partial derivatives. And by the way, qx and py are actually partial derivatives. See, I want you to make sure, you know, when you write dx and dy, these are not partial derivatives, right? But qx and py are actually the partial derivatives of the respective components. Py is 3y squared. What happened? Let's see. Py is 3y squared, and therefore qx minus py is 3x squared plus, go ahead, I'm going to write this down, minus 3y squared. So it's only 3x squared. That's nice. And that's what goes in here. Okay, so this turns out to be the integral. Now let's go ahead and define what this region R is. The you remember, x goes from 0 to 1. Okay, and for each x, y goes from the lower bound, which is x squared, and upper bound, which is x, right? Because x squared is below the straight line y is equal to x between 0 and 1. So this is my the limits. These are my bounds for the integral. And then what you are integrating is 3x squared. And of course, the way you rewrote this, x is outside, so the order is dy dx. Okay, so again, remember here, we have to go back to what we learned in chapters 5 to solve the right-hand side of Green's theorem. So this turns out to be, let's integrate this with respect to y. Well, nothing changes. Okay, it's x minus x squared. And now it is a calculus 1 problem. 3x cubed minus 3x to the fourth. This is what you have to integrate, and that's 3/4 x to the fourth minus 3/5 x to the fifth, integrating from 0 to 1. So that's 3/4 minus 3/5. And you can still do this, even though it's been a while since you learned how to subtract fractions. It's, what is that? It's 15th over 20 minus 12 over 20, which is 3/20. And you say, yay, I got the same answer, right? Notice here, it didn't take me a lot of lines to write this, okay? So the advantage of Green's theorem is, of course, it depends on, what qx minus py is, but many times this is simple. And if that's a simple integrand, you can do this much quicker than what you were doing in the old-fashioned way. Okay, so the nice thing about Green's theorem is you can find the work integral around the boundary of the region R simply by integrating what we know as the curl of f over the region R, which involves double integral. Now, let me just tell you what's going on here. Okay, so we have this counterclockwise oriented curve C, right? And the region R is inside here. And what happens is you can think of this partition of the region R. All right. And then, of course, you pick a point. This is exactly what you did when you studied the Riemann sum. And for each subregion or each, the subregion, you can pick a point, and then we can find qx minus py, which is called the curl. And later, in the next section, we will learn that the curl of a vector field actually tells you how much is going around. So it is the sort of like the tendency of the vector field f to go around this point xy, right? And so it's going to tell you like how much work is done as you go around the boundary of this small rectangle. But then you do the same thing over here, and notice here, as you do that, from one side it's going from left to right, and from the other side it's going from right to left, and they all cancel each other. Okay, you see that? If you keep adding all of these things for every single subregion, and in every single subregion we are going counterclockwise along these four edges. Okay, and that's what the curl of f in this case, which is qx minus py, is trying to express. And so when you add up all of these curls, which is basically what you do when you integrate the curl, which is qx minus py, everything gets killed. Everything gets canceled on the interior edges, right? Because like this edge is counted from top to bottom on this one, and then bottom to top on this other one. And so what happens is the only thing that remains, okay, after everything is canceled, is what happens on the outer edges. These are going to still remain. And so that's why the left-hand side, which is the work integral around the boundary, okay, is equal to the sum of all of these, the continuous sum, which is the integral, the sum of all of these, the values of the curl of f taken at each of these points in the inside of R. Okay, so keep this in mind, because sometimes you get a little confusing, right? So for instance, if you have something that's not simple, simply close. Okay? If the region R is bounded like this way, what in the world is this? Okay, remember this is a region that's connected, because R clearly doesn't have two separate components. It's closed. No, it's connected, but it's not simply connected because there's an empty hole in the middle, right? So in the case like this, we oriented C this way, right, counterclockwise. But remember, when you go around like this, if you think of all the points and the counterclockwise direction, the inside circle is actually oriented clockwise. Okay, it's a minor point, but since the one of the questions in your homework refers to this, I am just telling you this, right? So if you orient the outside circle or the boundary in the positive direction or the counterclockwise direction, then the inside circle will be oriented in clockwise orientation when you apply Green's theorem. So just keep that in mind. This may be useful sometime. All right, I'm going to ask you another question and give you time to work on that. And then we will come back and discuss how to do this. All right, I want you to find work, period. No, find a job. No. Okay, find work. Sounds like go get a job. But find work done by this vector field f, which I am going to write here. Y cubed, comma, x squared plus 3xy squared. Okay, over the circle, which is I'm going to give you the I'm just going to give you the parameterization, because we can all agree on parameterization. 3 cosine t and 3 sine t. So this is a circle of radius 3 centered at the origin, right? And t goes from 0 to 2 pi. So in a sense, what I'm asking you to do is this. You have a circle of radius 3, conveniently drawn, okay? And let's go ahead and draw this. All right, so you have a circle of radius 3, and of course, with this orientation, I mean, t is going from 0 to 2 pi, so this is, of course, the counterclockwise, oriented counterclockwise. And so this is my curve C. And the question is, how much work is done by this vector field F as you start from this, going around the circle once and comes back? All right, so think about this. Now, I would not try the old way in answering this question. Go ahead and apply Green's theorem and see. And when you come back, I will show you why you do not want to do this in the old way without Green's theorem, and how Green's theorem would be much nicer. I might give you a much nicer approach to solving this problem. All right, so when you think you get your answer, then you can go to the second part of this video.